In part 2, chapter 2, this section will involve information on neutrons and protons and their discovery, Avogadro's number and its relationship to the atomic mass unit. We'll talk about isotopes, their symbols and meaning, and then we're going to relate atomic masses to the different isotopes and the experimental determination of masses of isotopes are done in a mass spectrometer, and then it will lead up to the development of the periodic table. I think there's 4 parts to chapter 2, so this is the second one. All right, we'll start with discussion here on Avogadro's number. Avogadro lived between 1796 and 1856. The number associated with his name is 6.022 times 10 to the 23rd. And you can think of it as being just a number, kind of like a dozen. We know that word means 12. So in this case, Avogadro's number means 6.022 times 10 to the 23rd. It's just a number. It's a name for a number. And that particular number is associated with the link between measurements done on the nanoscopic scale. By that I mean we can look at the masses, for example, or the sizes of just a couple of electrons or a couple atoms, versus the macroscopic world where you can hold a gram of carbon, for example, in your hand. So, how many particles are in a gram, and we use Avogadro's number as that link. And he had the concept, but Benjamin Franklin, of all people, was interested in this concept, and he actually came up with some of the first experiments to measure the value. So if you have a gram of substance, how many atoms are present in that. And we won't go into detail on Ben Franklin's experiments, but they're not that difficult to understand. You can Google them and ask me about them if you'd like to talk about that. All right, so the AMU stands for the atomic mass unit, and if I wanted to talk about the mass of a carbon atom versus a mole of a carbon atom, I would be using AMU for the mass of an atom or two, or a small quantity. And there's a little bit of detail here, but hopefully you can see what the connection is between the mole, the AMU, and molar mass. So we start here with the mass of a carbon-12 atom. Now this symbol means that there are 6 protons. All carbon isotopes have 6 protons. The difference between these two numbers is 6, so this particular isotope has 6 neutrons. So the number on the top here is the sum of the number of protons and neutrons. In this case, 6 plus 6 is 12. All right, so you have a carbon-12 atom, an atom of the carbon-12 isotope. The definition of the AMU is 1/12 the mass of that. Okay, so then you can say 1 AMU. Now this is determined by measurement. These are these experiments and originally proposed and attempted by Benjamin Franklin. Okay, so the AMU, the relationship between the AMU and the gram is this number. So it's 1.6 times 10 to the minus 24 grams. So the AMU is a measurement of mass, and this is the relationship to the number of grams. All right, now if you divide this side, both sides, by 1.6 10 to the minus 24, you're going to get 1 over 1.6 times 10 to the minus 24 would be equal to 1 gram. So that's what's shown here. You just divide both sides by 1.6 10 to the minus 24. So then you get the number. This is Avogadro's number, 6.022 times 10 to the 23rd AMU associated with 1 gram. Now again, up to this point, this is about measurement of mass. So the relationship here is 1 gram is 10 to the 23rd AMUs. So here's the first time we see Avogadro's number. So we just give it that name. And then in general, we say that it's the number of items, and you can have an Avogadro's number of atoms or molecules, electrons, neutrons, anything. It's just a number. So then we say, because the AMU is 1/12 the mass of carbon-12, then the mass of one carbon-12 is going to be equal to 12 AMU. So we say that's a definition, but it really is based on the measurement up here. All right, and then the mass of 1 mole of carbon-12, you can think of it this way. Okay, so one carbon-12 atom weighs 12 AMU. And then you take this number, 6.02 times 10 to the 23rd carbon-12 atoms. That's going to be defined as a mole. So we have our definitions here. You can say, 12 AMU equals 1, the mass of 1, so the ratio of these two is 1. These two are equal, so the ratio of those two equals 1. And that's what we're doing here, just kind of stringing along these definitions. And we're doing it so that the units cancel. Okay, so you can have, let's see, carbon-12 atoms cancel here. And up to this point, we've got AMU per atom. Then the next thing is we take our mass measurement and say 1.66 10 to the minus 24 grams is equivalent to 1 AMU. And when we just set it up this way, you'll see the method to my madness here in a moment. The AMUs cancel, and now we have how many grams there are associated with a mole. So we end up with this number on the right with those units. All right, so the point of this is to say that, let's erase some of this here. Oops, yeah, okay. That one atom of carbon-12 weighs 12 AMU, and here 1 mole of carbon-12 atoms weighs 12 grams. So then, what's the relationship here to the periodic table? If you go to the periodic table, you look at the mass of carbon, it's actually 12.011. So that mass is kind of the mass of the kind of weighted average of masses for the isotopes. We're going to look at that by the end of this section. But in other words, you can go to the periodic table and you can say, all right, the mass is 12.011 grams per mole of carbon-12 atoms, or you could say 12 grams per 1 atom. So those two, anytime you look at the mass in the periodic table, you can use either set of units. So you can use grams per mole, which we usually do, or you could say, all right, well, it's 12.01 on average AMU per atom. And you'll see a reference to that as we go along. So the end here says that, whoops, where'd that come from? Carbon-12 atoms weigh 12 grams per mole. Carbon-12 atoms weigh 12 AMU per atom. All right, so now I talked about isotopes on the last slide, but here is the slide on it. And we have our symbol. This is just kind of the generic symbol for the isotope. And we use Z as the atomic number. That's going to be defined as the number of protons. A is the mass number up here, and that's the sum of the number of protons and neutrons. And isotopes of the same element differ in the number of neutrons. So you can have, for example, carbon has 4 isotopes. And you have carbon 11, carbon 12, carbon 13, and carbon 14. So those are the 4 isotopes. Notice that each one of the isotopes of carbon has 6 protons. Put some lines here. And that's indicated in the lower left. What's different is the number of neutrons, right? So the number of protons for the 4 isotopes of carbon stays the same. You take the difference between the atomic number and the mass number, and that gives you the number of neutrons. In the case of carbon-14, there are 8 neutrons, carbon-13, 7. Then we have 6 and 5 neutrons. So that's the difference. The number of electrons is the same. As the number of protons. So 6, 6, 6, and 6. Now if you've got carbon, charged, carbon plus or carbon minus, then the number of electrons are going to change, but not in this example here. So the difference between the different isotopes of carbon is the number of neutrons. And the 2 isotopes that are most abundant are these 2 when you find the naturally occurring sample of carbon. The carbon-12 and carbon-13, they're referred to as stable isotopes. The other 2, carbon-11 and carbon-14, are both unstable or radioactive, and in time they decay through a nuclear reaction to form other isotopes of different elements. And carbon-12 is about 99% naturally abundant. Carbon-13 is slightly less than 1% natural abundance, and these are way less than 1%. Okay, so then we have isotopes of the same element have different masses. A naturally occurring sample of an element usually contains more than one isotope of that element. You can look up table of isotopes on Wikipedia. You will see how many isotopes there are for each element. All right, on this slide, this is a little bit complicated, but this mass spectrometer is a very important instrument for chemists and physicists when we want to determine masses of isotopes. That's what I'm going to explain here, but you can actually use it to determine masses of molecules, atoms and molecules, very complicated molecules as large as proteins, for example. The resolution on the current day mass spectrometers is very, very high, very precise. All right, we'll talk about the general principle here. So you have your sample. Let's say it's carbon, naturally occurring carbon. Okay, so we put maybe some graphite in here. That would be carbon, stable form of carbon. And then you can see that it's heated up in this chamber. This is another one of those cathode ray tubes, but the shape of it is different. In this section here, you have the electric plates, just like we did before. You have the cathode and the anode. Over here is a magnet, so anything charged is going to be deflected during an electric or magnetic field. And what's happening in this region right here is that the electrons are being removed from the rest of the isotope. So if you have carbon-12, for example, if you have carbon-12 during this region between the electrically charged plates, the electron gets removed, so you get carbon plus an electron. Okay, now the way this is set up, this end is negative and this end is positive, and so the electrons are going to move in this direction and get picked up in this region. And then the positively charged particles are going to move in the opposite direction. So they're the ones that are being sent through this magnetic field and then off to this detector over here. And if you have a naturally occurring sample of carbon, for the most part, you're going to have carbon-12 and carbon-13, but the other isotopes are there as well. In this particular figure here, let's pretend that we've just got 3 isotopes of carbon present. And so each one of these charged isotopes, when it comes through, will have a different mass. So in other words, you've got carbon-12 plus, carbon-13 plus with one more neutron, right? And then carbon-11, whichever one it is. So they differ by the number of neutrons. And then The effect in the magnetic field depends on the mass. Remember, we talked about the E over M ratio. So the charge to mass ratio. In this case, the charge of each one of the isotopes is the same. It's +1, but the masses are different because the number of neutrons are different. All right, so think about it. So we say, we use the symbol alpha here for the angle of deflection. Through the magnet, the degree of the curvature. And so the ones that are lighter are going to curve more. The ones that are heavier are going to curve less. Kind of makes sense, right? So the ones with the heavier mass, the larger mass, are going to have a smaller angle of deflection. So that would be like this, a smaller angle of deflection. It's not curving so much. But the lighter ones, the ones with the smaller mass, are going to have the larger angle of deflection, so they're going to bend more and end up over here. Now this detector here is calibrated wherever these particles hit on the detector, there's a certain mass associated with it, and that's because the position for carbon-12 is known, and then you look at the positions of all the other isotopes relative to it. And you can put any isotope you want in here. You can take iodine and fluorine and uranium, anything, any isotope, put it through, and the mass of the isotope is measured relative to carbon-12 isotope, which is the standard, and that just means it's going to hit in a different position on the detector plate. And it's known, it's calibrated, so we know what those masses have to be. All right, so this is the situation for the mass, determination of the mass of carbon-13 relative to carbon-12. So based on the position on the detector, we know that the mass of carbon-12 is 1.0836 times the mass of carbon-13. And in fact, nowadays the number is known more precisely than this, but you can already see how precise that number is. All right, take both sides, multiply the mass of carbon times both sides of the equation. So then you isolate out the mass of carbon-13. The mass is equal to the mass of carbon-12 times this number. Multiply it out, and then you get the mass of the carbon-13 isotope relative to carbon-12. So this slide has the most details. We're going to be doing two calculations here, and it'll tie together some of the concepts that I've already talked about for this section 2. And so we'll start with example 1, A and B. And what is the molar mass of a naturally occurring sample of bromine, given that the 79 isotope has a mass of 78.91 and so on, AMU, and is 0.5069 abundant? That means 50.69% abundance. And you've got the other isotopes, so there's the two isotopes, 79 and 81. And the 81 isotope has a mass of 80.91, etc., AMU, and is 49.31 abundant or 49.31% abundant. All right, and then we'll get to part B. So let us get a clean whiteboard page. That. Oh wait, I'm sorry, we didn't do the second part, part B. So if we have a sample of naturally occurring bromine is 50 grams, what masses are due to the 79 and the 81 isotopes? All right, we know that it's about 50-50. It's not exactly 50-50, but if you've got 50 grams, it's going to be about 25 grams of 79 isotope and about 81 grams of the 81 isotope. About 25 grams of the 81 isotope. It's about that, but that's not good enough. We've got the precise abundance, so we want to use that. So then we're going to take the abundance, instead of saying 50%, it's 50.69% of the 50 grams will be associated with the 79 isotope, and then 49.31% of the 50 grams will be associated with the 81 isotope. So that's how you would do it. Go back and look at example 2 here, and this one is chlorine. Similarly, we're going to look at the 2 isotopes of chlorine. One is the 35 isotope, the other one is the 37 isotope. And in this case, we're given the molar mass in terms of AMU. We could say, we look in the periodic table, we're going to find 35.453 grams per mole, or AMU. And by the way, that molar mass that we calculated for bromine just a minute ago, you look in the periodic table, you're going to see that we've got an exact match for the number there. All right, so in this case, we're given the molar mass. We can look that up, periodic table, and we know the masses of the 2 isotopes, and the question is, what are the abundances? So we're going to work backwards on that one here and go through the details. So bromine has 2 isotopes, and I'm going to just tabulate here information. The first isotope is bromine 79, and the other isotope is bromine 81. Okay, it has 35 protons, and the difference between top and the bottom, the atomic number and the mass number, is the number of neutrons. So, excuse me, we can maybe say that, the name of the isotope is the 79 isotope, and the 81, the name of the isotopes. All right, we're given the mass of the isotope, in the problem, masses 78.918336 AMU and 80.916289 AMU. And then the percent abundance, we want to put it in percent. Don't have to do that. 50.69% of the 79 isotope and 49.31% of the 81 isotope. Okay, it's nice to tabulate that information. So how do you get the mass that's in the periodic table for bromine? How do you get the molar mass that's in the table? So we say that it's a weighted average of the masses of the isotopes of bromine. In this case, bromine has 2 isotopes. And the weighted average means we're looking at the percent abundance of each one. So our equation then is going to be molar mass in the periodic table. And you take the abundance, put it in decimal form, 0.5069 times the mass of the isotope, 78.918 336 plus 0.4931 times the mass of the 81 isotope, which is 80.916289 AMU. And that will be equal to 40.004 plus some more decimals, and then 39.900, more digits, I should say. Now, I wrote out 5 sig figs for each one because the abundance is known to 4 sig figs, so We don't want to round at this point, but we do want to note that this answer, this part of the answer has 4 sig figs, and this part of the answer has 4 sig figs as well because of the 4 sig figs here and here. All right, then you want to add them together, and in this case it's going to be 79.904, and then we're going to be rounding right here, so this will be equal to 79.90. And you can say AMU, which would be kind of the weighted average for a particular bromine atom, or you can say 79.90 grams if you happen to have a mole of bromine atoms. So grams per mole would be the unit that we use most often for the periodic table. All right, 79.90 grams per mole. All right, the next example is the chlorine one. So let's back up into that problem. So for part B, we would say that 0.5069 or 50.69% of the 50 grams total would be equal to 25.345 grams of the 79 isotope, and that is, okay, I've calculated that. And then the other one is 0.4931 times 50 gram sample. And then this one is going to be 24.665 grams of the 81 isotope in the 50 gram sample. So if you add up these two, you're going to get 0.00005, and you're going to round to that. So 50.00 grams total, which is what we would have expected. All right, so it's about 25 grams of each, but we know we can do better than that. We have the natural abundances. All right, so let's go ahead and do the chlorine on a new page here. So this one would be number 2, and we could do a similar table here. We have the chlorine 35 isotope and the chlorine 37 isotope, and we can call it the 35 isotope and the 37 isotope. Now we know the masses of the isotopes. Oops, should probably not put that line in there yet. 34.9623 AMU and 36.29321 AMU. And for some reason we know the AMU on the chlorine 35 to 1 more sig fig. All right, and then we're after the percent abundance. Okay, we don't know that. That's what we want to know. All right, so we're going to set it up the same way. We're given the molar mass in the problem as 35.453 grams per mole, or you can say AMU, and I guess we'll say AMU for this. So we set up the problem as 35.453, that's the molar mass, and actually we're going to call the abundances X and Y. Whatever those numbers are. It's easier to think about it that way. So X percent, or put it in the decimal form, the X is the abundance. times 34.9623 AMU plus Y abundance times 36.29321 AMU. That's our equation. Now we cannot solve this problem because we have one equation with two unknowns. In order to solve it, we need another equation involving x and y. And if you think about it, if you have just two different isotopes, the sum of their abundances has to be 100%, or in decimal form it would be equal to 1. And if you look back to the bromine problem, you'll see that the sum of the abundances equals 1. Okay, so we're going to develop a second equation here. 1 is equal to x plus y. And then we can solve for y and say that is equal to 1 minus x. All right, and then we're going to substitute y here as 1 minus x. So we'll rewrite it. And it'll be 35.453 is equal to 34.9623 x plus 36.29321 times 1 minus x. Make sure you don't put x minus 1 there. So then you have 35.453. We had two equations and two unknowns, so now we can solve it. 34.9623x. Then we're going to distribute here. 36.29321 minus 36.29321x. And you know what? If I go back into my notes, I actually have 6923. No, that's right. That's what I have. Okay, never mind. Okay, so now we're going to combine, we're going to combine the numbers that are multiplied by x on one side and then the numbers without x on the other side. So when we do that, we are going to have 35.453 minus 36.29321 is equal to 34.9623x minus 36.29321x. And when you have that, you end up with a negative 0.84021. And you have it's known to 3 decimal places there. So in other words, I'm looking at 3 decimal places versus 5 decimal places. So when you round, it'll be this place right here. Okay, then that'll be equal to negative 1.33091 x. So then when you solve for x, you're going to get 0.84021 divided by 1.33091, and this is equal to 0.63130. 3 sig figs in the answer using multiplication division rule, and 0.631 would be the answer. So for this one then, x is equal to 63.1%, and x is the abundance of the chlorine 35 isotope. Okay, so you could say 63.1% abundance of chlorine 1735 isotope. And then you could say 100 minus that, or you could say, pretty much that way. You want to say 100. So 100 minus 63.1% is going to be equal to 36.9%. I guess what I was going to say, or you could say 1 minus 0.631 is going to be 0.369. So you could do that either way, but in any event, that will be for the chlorine 37 isotope right there. All right, this one is a much more challenging calculation than the one we did for bromine. What do you think? Which one do you think I would ask you for in a test? Probably this one is a little bit more challenging, and you've got group activity for this section, and I think there's a couple of problems that are similar to this one that you can practice with. All right, I believe that is the end of this section.